Here's something that should bother you more than it does. Right now, as you sit watching this video, you are spinning, not just because the Earth is rotating beneath your feet at roughly 1,600 kilometers per hour, not just because the Earth is simultaneously orbiting the Sun at nearly 30 kilometers per second, but because the entire solar system is sweeping through the Milky Way at over 200 kilometers per second. And the Milky Way itself is hurtling through the cosmic web in a slow, majestic spiral that has been turning for billions of years. Everything is spinning, and nobody asked it to. That's the mystery that almost nobody thinks to ask about. We talk about what's out there, the black holes, the galaxies, the dying stars, but we almost never ask the one question that sits underneath all of it. Why does any of it rotate at all? Where did this cosmic spin come from? And what would happen to the universe if it just stopped? The answer will take you on a journey from the very first microseconds, after the Big Bang, through the birth of galaxies, all the way to objects so dense and so fast spinning that they literally drag time itself around with them. And somewhere in the middle of all this, you'll realize that the reason life exists on this planet, the reason you exist, comes down to the fact that some gas clouds, billions of years ago, started spinning in just the right way. Let's start at the very beginning, and I mean the very beginning, when the universe was born, roughly 13.8 billion years ago. It didn't just explode into existence and sit there politely. The infant cosmos was a seething, churning ocean of energy and matter, expanding at a rate our brains weren't built to comprehend. And hidden inside all of that chaos was the seed of every spin, every orbit, every rotation you've ever seen or ever will see. The seed was something called a sim. Here's what that means. In a perfectly uniform universe, one where matter was spread out with absolute evenness, in every direction, nothing interesting would ever happen. Gravity would pull equally from all sides. Every particle would be tugged in perfectly opposite directions with equal force. Everything would stay exactly where it was. The universe would be a featureless fog, eternal and dead. But the universe wasn't perfectly uniform. It never was. In the first moments after the Big Bang, tiny quantum fluctuations, variations smaller than an atom, created microscopic differences in the density of matter. Some regions had ever so slightly more particles crammed in. Others had slightly fewer. These weren't dramatic differences. We're talking about variations so small they would have been invisible to any instrument we could build today. But those tiny differences were enough to change everything. Because once you have uneven density, you have uneven gravity. And once you have uneven gravity, things start to move. And crucially, they don't move in straight lines. They move in ways that nudge, tug, and twist. When a cloud of gas begins to drift toward a region of slightly higher density, it doesn't fall in like a perfectly aimed arrow. The surrounding matter is also pulling at it from different angles. And so instead of a clean, direct collapse, the gas begins to veer, to curve, to develop a slow, barely perceptible rotation. Now, here's the part that makes physicists smile. In space, there is no friction. On Earth, we take friction for granted. You spin a top on a table and it eventually wobbles to a stop because the table is constantly stealing tiny amounts of energy from it. Throw a ball in the air and their resistance slows it down. Every rotation we see in daily life gradually bleeds out its energy into the environment. In the vacuum of deep space, that bleeding doesn't happen. Once a cloud of gas picks up the slightest hint of rotation from those early asymmetries, that rotation is locked in. It doesn't decay. It doesn't fade. It just keeps going, growing more organized as gravity pulls the cloud together, waiting for the moment. Millions of years later, when that rotation will build an entire solar system. This is what physicists call the conservation of angular momentum. It's one of the most powerful and unbreakable rules in nature. And it's the reason why the universe isn't a featureless fog. Angular momentum, once created, cannot disappear. It can be transferred from one object to another, but the total amount in any closed system stays the same. Always. The conservation of angular momentum isn't just a rule written in a physics textbook. It's embedded so deeply into the mathematical structure of the universe that its existence can be derived from a more fundamental principle. The fact that the laws of physics are the same at every moment in time. The connection between these two ideas, symmetry and conservation, was worked out by the mathematician Emmy Noether in 19, and it remains one of the most profound insights in all of science. When you see a galaxy rotating today, you are witnessing a law of mathematics playing out at cosmic scale, a law so fundamental that it would hold in any universe with the same basic structure as ours. You've felt this rule in action, even if you've never heard of it. Watch a figure skater launching into a spin, with their arms stretched wide. They rotate slowly. The moment they pull their arms into their chest, reducing their radius, they suddenly explode into a blur of motion. Nothing pushed them faster. No new force acted on them. They simply preserved their angular momentum across a smaller body, and the result is an almost magical acceleration. The early universe did exactly this, but on an incomprehensibly larger scale. Those gently rotating gas clouds, under the patient influence of gravity, slowly contracted, and as they contracted, they spun faster and faster, just like the skater, pulling her arms in. What began as a nearly imperceptible whisper of motion became, over millions of years, a powerful cosmic vortex. A vortex that would eventually give birth to stars, planets, and everything on them. But rotation alone doesn't make a solar system. It doesn't even make a star. For that, something else had to happen. Something that turned the raw chaos of a spinning gas cloud into one of the most elegant structures in the entire universe. Think about what happens when you stir a cup of coffee. You drag a spoon through the liquid in a circle, and within seconds, the coffee and cream that were just sitting there begin to organize themselves into a swirling pattern. The outer parts of the liquid lag behind the inner parts. A spiral forms. Without doing anything deliberately artistic, you've created structure from chaos, purely through the mechanics of rotation. Nature does something very similar when a massive cloud of gas begins to collapse under its own gravity, but the result is far more dramatic. As the cloud contracts, it spins faster, as we just discussed. But there's a critical difference between the direction parallel to the rotation axis and the direction perpendicular to it. In the direction of the rotation axis, straight up or straight down through the spinning cloud, there's nothing pushing back. Gravity pulls matter inward freely, and the cloud flattens rapidly in that dimension. But in the plane of rotation, the situation is completely different. There, the centrifugal tendency of the spinning matter pushes outward, directly opposing the inward pull of gravity. Matter in the equatorial plane can't just fall inward. It has to fight its way in, and much of it never makes it all the way to the center. What you end up with is a disk, a flat, spinning, pancake-shaped structure with a dense concentration at the center. Astronomers call this an accretion disk, and it is, without exaggeration, one of the most important structures in the universe. The word accretion means the gradual growth of something by accumulation, and that's exactly what these disks do. They're not just flat, they're dynamic. Inside the disk, particles are constantly bumping into each other, spiraling slowly inward as they lose tiny amounts of energy to friction and collisions. The inner parts of the disk orbit faster than the outer parts, creating shear forces, layers of gas sliding past each other at different speeds. This shear generates heat, and heat means energy, and energy, concentrated in just the right place, can trigger something extraordinary. In the dense, hot inner regions of a protostellar accretion disk, the disk surrounding a star being born, temperatures and pressures eventually climb high enough to ignite nuclear fusion. Hydrogen nuclei begin slamming together fast enough to fuse into helium, releasing tremendous energy in the process. A star is born not from a collision, not from a single catastrophic event, but from the slow, patient, organized work of a spinning disk, funneling matter inward over millions of years until the conditions for ignition are finally met. And the disk doesn't stop there. The material that doesn't fall all the way into the newborn star continues to orbit around it. Over time, that orbiting material, dust, ice, rock, gas, begins to clump together through a process called small particles stick to each other. Those clumps attract more particles. The clumps grow into pebbles, pebbles into boulders, boulders into planetesimals, and planetesimals through billions of collisions and mergers into planets. This is why all the planets in our solar system orbit the sun in roughly the same plane. They didn't arrive there from random directions in space. They all formed from the same flat disk of material that surrounded the young sun. The solar system isn't just a loose collection of objects. It's the fossilized imprint of the disk that built it. The accretion disk is nature's most efficient factory. It takes raw, chaotic material and uses the twin forces of gravity and rotation to sort it, concentrate it, heat it, and shape it into something structured and permanent. Without the accretion disk, you don't get stars. Without stars, you don't get the heavy elements that make up planets. Without those elements, you don't get chemistry. And without chemistry, you don't get life. There's another detail about accretion disks that doesn't get nearly enough attention. The fact that they're flat. The fact that matter organizes itself into a thin plane rather than a spherical blob has profound consequences for how efficiently matter can actually reach the center. In a spherical distribution, particles can approach the center from any direction, but they're constantly being deflected and scattered by each other. Very little actually makes it through to the core. In a disk, however, the geometry forces particles to approach through a narrow plane, creating a kind of organized traffic system. The collisions that do happen are productive. They strip away angular momentum, allowing particles to gradually spiral inward instead of just bouncing randomly around. This is the mechanism by which a disk feeds a growing star. And it's also, on larger scales, the mechanism by which a disk feeds a growing black hole. The accretion disk surrounding a supermassive black hole works by exactly the same principle as the disk surrounding a newborn star. Matter spirals inward, loses angular momentum through friction and collisions, heats up to temperatures of millions of degrees, and eventually crosses the event horizon and disappears. The difference in scale is enormous. The physics is the same. Rotation, in both cases, is the invisible hand controlling the rate at which matter makes the final plunge. You'll see galaxies, enormous, breathtaking, slowly turning islands of hundreds of billions of stars, each one separated from the next by millions of light years of empty space. And they're spinning too. The same principle that makes a protostellar disk also operates at the galactic scale. The early universe wasn't just made of individual gas clouds. It was structured into vast filaments and sheets of matter, threaded through an even vaster cosmic web. Within this web, enormous concentrations of gas, containing enough material to make hundreds of billions of stars, began to collapse under their own gravity. And just like the smaller clouds we discussed earlier, they were never perfectly still. They always carried the imprint of those early asymmetries, that faint original rotation impressed on them at the very dawn of cosmic time. As these massive structures collapsed, their rotation amplified. The gas arranged itself into a disk, a galactic disk, far larger than anything in a single solar system, but built by the same physics. Stars formed in waves throughout this disk, generation after generation. The disk itself became the Milky Way, the Andromeda Galaxy, the countless spiral galaxies you see in deep-field telescope images, their arms curling gracefully outward like the pattern of cream stirred into coffee. But here's where the story takes a deeply strange turn. In the 1970s, an American astronomer named Vera Rubin was carefully measuring the rotation speeds of stars in spiral galaxies. She was expecting to find what common sense predicts that stars near the outer edges of a galaxy would orbit more slowly than stars near the center. The same way the outer planets in our solar system orbit the sun more slowly than the inner ones. This is called Keplerian rotation, and it follows directly from Newton's laws of gravity. What she found was completely different. The stars at the outer edges of galaxies weren't orbiting slowly. They were moving just as fast as stars much closer to the galactic center, in some cases faster. This shouldn't be possible. If the only matter in the galaxy was the visible matter, the stars, gas, and dust you can actually see, those outer stars would be moving far too fast to stay in their orbits. They should have been flung off into intergalactic space billions of years ago. They weren't. they stayed, which meant something else must be holding them in something with gravity, but something completely invisible to any of the telescopes available at the time, or since. This invisible substance became known as dark matter, and while we still don't know exactly what it is, despite decades of searching, we know what it does. It forms a vast, invisible halo surrounding every galaxy, extending far beyond the visible disk of stars. Its gravitational influence keeps the outer stars of galaxies from flying away. It provides the hidden scaffolding that makes the graceful spiral arms of galaxies. Carved into shape by the combined action of rotation and dark matter's gravitational pull over billions of years. Think about what a gyroscope does. A spinning top, once set in motion, resists being knocked over. It maintains its orientation. It's stable in a way that a non-spinning top simply isn't. The rotation of a galaxy does something similar at cosmic scale. It gives the galaxy a kind of rigidity, a resistance to being disrupted. Without rotation, a galaxy would be little more than a loose, formless cloud of stars, vulnerable to any passing gravitational disturbance. With rotation, it becomes a coherent structure, capable of maintaining its shape for billions of years, while billions of stars are born, live, and die within it. And rotation does something else at the galactic scale that is crucial for everything that follows. It creates dense regions as stars orbit within the galactic disk. The gravitational and rotational dynamics concentrate matter in certain areas, particularly toward the center. Over time, these concentrations grow extreme. In the cores of most large galaxies, including our own, this process eventually produces the most dramatic objects in the known universe. Black holes. Not just any black holes, but supermassive ones. Titans dot the Milky Way's central black hole, called Sagittarius A*, contains roughly 4 million The monster at the center of the galaxy, M87, famously photographed by the Event Horizon telescope in 2019, contains more than 6 billion solar masses. These objects spin. Of course they do. Everything spins, and black holes are no exception. But when a black hole spins, it doesn't just sit there passively rotating like a planet. It does something far stranger. It drags the very fabric of space and time around with it. This is a prediction of Einstein's general theory of relativity, and it has been experimentally confirmed. The formal name for the effect is frame dragging, sometimes called the lens-stirring effect after the two physicists who first calculated it. The basic idea is this. In Einstein's universe, space and time aren't a passive backdrop against which events unfold. They're a dynamic medium, a fabric that can be warped, stretched, and twisted by the presence and motion of mass. A rotating mass doesn't just warp space by sitting there, it actively twists it. It drags the surrounding space-time around itself like a stone dragged through thick honey, creating a swirling vortex not in any material substance, but in the geometry of reality itself. Imagine what it would be like to be near a rapidly spinning black hole. Even if you fired your rocket engines with everything you had in a direction perpendicular to the black hole's rotation, you would find yourself being slowly swept sideways around the black hole, regardless of your intentions. The space you're moving through is itself rotating, carrying you with it whether you like it or not. There is no straight line anymore. The very concept of going straight breaks down in the presence of extreme rotation. This region of dragged space-time around a rotating black hole has a name, the ergosphere, and it has a property that seems almost too strange to be real. Inside the ergosphere, it is physically impossible to remain stationary relative to the distant universe. You cannot hold your position. You are always being carried around. Movement in the direction of the black hole's rotation isn't just easier inside the ergosphere. It's mandatory. This is rotation taken to its absolute logical extreme. At the scale, spin isn't just a property of matter, it's a property of space itself. But black holes aren't the only objects in the universe where rotation becomes extreme enough to bend reality. There's another class of objects smaller, more numerous, and in some ways even more astonishing that demonstrates the power of rotation with almost clockwork precision. When a massive star reaches the end of its life, it doesn't go quietly. After burning through its nuclear fuel over millions of years, the core of the star, no longer supported by the outward pressure of nuclear reactions, collapses catastrophically. In less than a second, a core the size of Earth compresses into a ball roughly 20 kilometers across. The density of the resulting object is almost beyond comprehension. A single teaspoon of its material would weigh billions of tons. This is a neutron star, and like a figure skater pulling her arms in, the collapse amplifies whatever rotation the original stellar core possessed into something extraordinary. The resulting neutron star can rotate hundreds of times per second. Some of the fastest ones, called millisecond pulsars, complete over 700 full rotations every single second. 700 rotations per second. The equatorial surface of such a star is moving at a significant fraction of the speed of light. Neutron stars have another remarkable property. Their powerful magnetic fields, combined with their rapid rotation, generate intense beams of electromagnetic radiation, radio waves, X-rays, that shoot out from their magnetic poles. Because the magnetic axis is often tilted relative to the rotation axis, just like Earth's magnetic North Pole isn't exactly at the geographic North Pole. These beams sweep through space like lighthouse beacons as the star rotates. If Earth happens to lie in the path of one of these sweeping beams, we detect a pulse of radiation each time the beam sweeps past us. These objects are called pulsars, pulsating stars, and they are among the most precise natural timekeepers in the known universe. Some pulsars tick with a regularity that rivals atomic clocks, losing less than a microsecond per year. Astronomers have put this precision to work in remarkable ways. By carefully monitoring the arrival times of pulsar signals, researchers have detected the influence of gravitational waves, ripples in space-time, long before instruments like LIGO were sensitive enough to detect them directly. The first indirect evidence for gravitational waves came from observing how the orbit of a binary pulsar system slowly decayed over years, exactly as predicted if the system was radiating energy away in the form of gravitational waves. The two discoverers of this binary pulsar, Russell Hulse and Joseph Taylor, were awarded the Nobel Prize in Physics in 1993. Rotation, in the case of pulsars, has become a measuring instrument. The spin of a collapsed stellar remnant serves as a cosmic clock, precise enough to test the deepest predictions of Einstein's theory of gravity. There is something almost philosophical about this. The rotation that began as a tiny asymmetry in the density of matter less than a second after the Big Bang, a barely perceptible whisper of motion in the primordial gas, has been amplified over billions of years into something capable of measuring the very curvature of spacetime. The universe uses its own spin to examine itself. But let's bring this home. Let's talk about what all of this means for you. You live on a rocky planet, orbiting a medium-sized star in the outer arm of a spiral galaxy. Nothing about that sentence sounds particularly special, but hidden in every single word of it is a dependency on rotation that, if broken at any point, would make your existence impossible. Let's start with the sun itself. It formed from a rotating disk of gas and dust. As we discussed, the rotation of that protostellar disk is the reason there is a solar system at all, rather than just a single, slightly larger star surrounded by a thin haze of gas. The disk structure allowed heavy elements, carbon, oxygen, iron, nitrogen, to concentrate and accumulate rather than being blown away or absorbed. The rocky planets, including Earth, are made of material that could only form and collect because of the organized, slow dynamics of that disk. Now, think about Earth's orbit. The reason Earth doesn't just fall into the sun is because it's moving sideways fast enough that it keeps missing it over and over again, year after year. This perpetual falling around the sun is what an orbit is. The speed at which Earth orbits is a direct inheritance of the angular momentum contained in the rotating disk that formed the solar system. Slightly less angular momentum in that original disk, and Earth's orbit would be smaller, closer to the sun, hotter. Slightly more, and Earth would be farther out, colder. The fact that Earth sits in the habitable zone The narrow band of distances from the sun where liquid water can exist on a planetary surface is not just luck. It's the result of rotation doing its job with precisely the right amount of energy. Then there's the rotation of Earth itself, the 24-hour day, the alternation of sunlight and darkness, the tidal interactions between Earth and Moon that have gradually slowed Earth's rotation to its current rate over billions of years. All of this creates the thermal cycling, warm days, cool nights, seasonal shifts that drives the weather patterns, ocean currents, and atmospheric dynamics that make Earth's climate livable. A planet that doesn't rotate, or rotates too quickly, or too slowly ends up with extreme temperature differences. Between its sun-facing and dark sides, violent, permanent storms at the terminator, or conditions hostile to the complex chemistry that life requires. But perhaps, most critically, consider Earth's magnetic field. Our planet has a liquid iron outer core that circulates in complex patterns driven partly by heat and partly by the Coriolis forces created by Earth's rotation. This circulation of electrically conductive liquid metal generates a magnetic field, the geomagnetic field, that extends far out into space and forms the magnetosphere. The magnetosphere is our shield. Every day, the sun blasts the inner solar system with a continuous stream of charged particles. The solar wind, moving at hundreds of kilometers per second. Without the magnetosphere, this solar wind would slam into the atmosphere, gradually stripping it away molecule by molecule. Mars, which lost its internal magnetic field billions of years ago, has spent those billions of years having its atmosphere stripped away by the solar wind. Today, Mars' atmosphere is less than 1% as dense as Earth's. Whatever oceans or rivers Mars once had are long gone. Earth keeps its atmosphere because Earth rotates. The rotation drives the dynamo that generates the magnetic field. The magnetic field maintains the shield. The shield preserves the atmosphere. The atmosphere sustains life. The chain of causation runs all the way back to that first whisper of angular momentum in a collapsing cloud of gas, billions of years before the Earth existed. Let's zoom back out, one final time, all the way out. We began this journey with a simple question. Why does everything spin? The answer turned out to be a story told across 13.8 billion years. And every scale of existence, from quantum fluctuations smaller than atoms to galactic structures hundreds of thousands of light years across, the spin in the universe didn't come from nowhere. It came from asymmetry, from the fact that the universe was never perfectly smooth, never perfectly uniform. Those tiny deviations in the distribution of early matter set the first particles moving in ways that weren't perfectly straight. And because space has no friction, because angular momentum cannot simply vanish, that motion was preserved, passed down, amplified, organized. The conservation of angular momentum is, in a sense, the universe's long-term memory. Every spinning planet, every orbiting moon, every rotating galaxy is carrying within its motion a memory of the conditions at the very dawn of time. The spin of the Earth, as it turns beneath your feet right now, is an echo. A very long, very amplified echo of a quantum fluctuation that occurred before the first atom had ever formed. Rotation turned chaos into structure. It transformed formless clouds of gas into organized, flat disks where matter could accumulate, heat up, ignite, and become stars. It kept galaxies coherent and stable across cosmic time. It powered the magnetic fields that made rocky planets habitable. It created the spinning remnants of dead stars that tick off time with such precision that we can use them to test the deepest laws of physics. And at its most extreme, rotation revealed something even more profound, that it isn't just a property of matter. It's a property of space-time itself. A fast-spinning mass doesn't just move through the universe. It reshapes it. It drags the geometry of reality around with it, creating regions where the usual rules of motion and direction no longer apply in the ways our intuition expects. Here is a thought I want to leave you with. The next time you look up at the night sky and see those stars, those distant, silent points of light, try to see them differently. Try to see what they actually are. Each one of those points of light is a massive, rotating nuclear furnace, held together by gravity and shaped by billions of years of dynamic, spinning evil. Each one is orbited by worlds that formed in a rotating disk, Many of those worlds are themselves rotating, generating the magnetic fields and stable climates that could, in principle, shelter some form of life. The night sky is an ecstatic painting. It's a living, rotating, perpetually in motion system that has been running continuously for nearly 14 billion years. And you, your atoms, your chemistry, your body, your consciousness, are the product of that system. You are what rotation eventually makes, given enough time and the right conditions. There's a beautiful humility in this realization. We often think of ourselves as separate from the cosmos, observers standing outside it, looking in. But the rotation that spins galaxies is the same rotation that built the sun, the same rotation that keeps Earth in its orbit, the same rotation that drives the dynamo in Earth's core, which powers the magnetic shield, which preserved the atmosphere, which allowed oceans to form, which let chemistry become biology. You are not separate from all of that. You are downstream from it. Every rotation in the universe, in some small but real way, contributed to the conditions that allowed you to exist right now and wonder about it. So the next time someone asks you why the planets orbit the sun, or why a galaxy looks like a spiral, or why we have seasons, or why Mars is a dead desert and Earth is alive, the short answer to every single one of those questions is the same. Because of rotation. Because of a law of nature so old and so fundamental that it predates the first star, the first atom, even the first nucleus. A law that has been running without interruption since before anything we would recognize as matter even existed. Everything spins, and everything you are is because of it.